Hey everyone, welcome to my channel. Today let's whiteboard the Ad Click Aggregator. So Ad Click Aggregator is a system to calculate, to count, or basically track all the clicks that a user or any user would make on a website when they click on an ad. So whenever you visit any website, you must have seen a lot of ads being displayed over there. So those ads are displayed by some company, some XYZ company who have put up those ads via Google AdSense or Facebook Meta ads. They just don't want you to click on it, but they also want to keep a track of how many users clicked, which website had the most number of clicks, which type of ad got clicked the most. And in this video, we'll design a system where we can keep a track of all that in our system, and at the end, so we display the ads on a page. Whenever a user clicks on it, we pass it to a stream where all those clicks somehow get calculated. We'll test that in a moment in this video. And at the end, when all these clicks are getting passed on via system getting processed, at the end we want to display a dashboard kind of a thing where the user is able to, or the admin of the company or whatever, they're able to see all the counts, they're able to track it via some sort of dashboard. Let's go ahead. Again, if I talk about what exactly are we building, the users go to a website, they click on an ad, then those clicks travels through our system, which we will be building. And at the end, the advertisers are able to read those metrics via some dash. And so if you look at it in this system, so every system design, whatever you work on, there are some functional requirements that we have to meet. So in this system, are you able to identify the two main functional requirements that we have? The first one is that the user should be able to, whenever the user gets clicks on the ad, the user should be redirected to the advertiser and should happen in real time, very fast, quick. There should be very low latency. And the second requirement is that the advertiser should be able to answer how many clicks happened this minute. I wanted to place some emphasis on this minute because this changes the course of the design, how we design it. So basically, they want a near live answer. They don't want how many clicks happen in an hour. They want it this minute. So we want to design a system which lets us do that. So these were the two functional requirements that we discussed. First was the user is able to track and redirect, and each ad clicks a click gets recorded and the user gets redirected. And the second is advertisers can query click counts over a time range, and it should be 1 minute granularity. And there are some things out of scope that I want to call out, and even if you're in an interview, you can call that out. So first is ad targeting. We are not trying to discuss how a particular ad gets shown on which page, or ad serving, how the ads are being served, anything about about the server of the ad, anything about fraud or spam detection. We're not going to discuss about that. We are not tracking cross device. So if an ad gets displayed on one device and somehow the user gets redirected to some other, we are not dealing with that here. And also conversion tracking. We are not really tracking if some user clicked on an ad and they actually made a purchase. So we are not tracking all of that. So these are unknown. Let's move forward. Now, the second most important part of any system design after the functional requirements is the non-functional requirements. So let's have a look at what all are the non-functional requirements in our system. So first, let's talk about the scale. So we are talking about 10 million active ads at any given moment. Per second traffic would be 10,000 clicks per second. So we can take it as 1K clicks per second, but for peak we usually consider a 10 time traffic of the average traffic, so it will be 10,000 clicks per second, which is the peak. And we can calculate it using this 100 million. If we have 100 million clicks in a day, which is about 100 into 10 to the power 6, each divided by 10 to the power to make it 10 to the power 5 to make it equal to converted to per second. So it comes out to be 100K per second, and that is what we discussed. So peak would be 10 times of this traffic that we get, right? And the fourth And the next requirement, so this was about the scale that we would be dealing with in our system. The next is how much latency we want to allow in our system. So we want to allow latency, query latency of less than 1 second. So we want to design a system where the data is stored efficiently and it can be queried efficiently. Along with that, we don't want any data loss to happen. So every click must be counted. It should be durable and it should be replayable. So in case, firstly, we should be able to ingest all of our data into our system. Nothing should be lost. And once we have ingested, it should be reliable that we have tracked it. In case any node gets down at any point of time, this should be designed in a way that it is replayable. Next, we already discussed about it should be near real time. So very less, the data should not be stale. They should be Advertisers should be able to see the clicks seconds after they happen. The third is idempotent. So the same click should not be counted more than once. And the next is fault tolerant. So if the nodes died or the network split, how do we ensure the accuracy of the count? So we need to ensure that the counts are accurate. We don't lose it, or just because the network blipped, we count any counts as twice or thrice. So that's not something we want in our system. So we want to design it in a way so that it stays accurate. So we are trying to handle four main functional requirements here. There should be no data loss. There should be real time. System should be fault tolerant, and we should not count any add click twice. So if you just try to think on a high level how the system would look like, just on a high level, we have some source from where we're getting a lot of clicks. Then we have some sort of engine where these clicks are getting stored. Just think on a high level, and then at the end we have some dashboard, and where the admin or the companies would be able to, or the advertisers would be able to see their data. So this is how we want to build it. So all we need to think about is how this aggregation engine is able to count the ad in a minute, all the ads in a minute. Let's look at the core entities that we would be working on within our system. So we have five main core entities. So let's start looking from the very start. We have a user who comes on a website. So and they click on a website. So we have an ad. So for that ad, we have ad ID, advertiser ID, redirect URL, and the campaign. These are the information that would correspond to that model. The next is impression. So we will talk more about what this impression means, but let's just for now consider unique ID per ad shown to a user. And this is how we would ensure idempotency, that a click is not counted twice. And this is the click event. So when a user clicks on that ad, the click event gets generated. So this talks about the impression ID, the ad ID, the timestamp at which the click happened, and so on. So these three happen when the user clicks on that ad. So we are still on the ad page, we have not moved forward. The next entity is the aggregate bucket. So aggregate bucket is basically when we want to, so the events are like one single event. Every click is like one event, but aggregate bucket is a combination of all those events per minute. So we, not just events, but every event would have some ad ID, the timestamp, and the impression ID. So we would club that. Each 1 minute, we would count the number of ad clicks for one particular ad, and so on. We will do for all the ad IDs, and that would what is called as aggregate bucket in this scenario. Right, so that is the fourth core entity. The fifth core entity is the advertiser. So advertisers are basically, so we may not even need to discuss this because we are not really going to use it. At the end, it's just what we are. The advertisers are the ones who are displaying those ads, so they own the ads. They can query those campaigns metrics. So eventually, whatever we are building for these advertisers. So they have to be able to see those ads on their side via a dashboard. So we can consider that as also another core entity. So let's move on. Now, there are two main endpoints that we would be handling in this system. The first endpoint is the click event. So, click is whenever a person clicks on an ad. So, that is the click event that we want to track. So, this is the first endpoint when the user clicks on an ad. And when we click on the slash click endpoint, we send these to the backend server, and at the as a response, we get 302 redirect to the advertisers. So you can take it like as we send this in the body, this is the client, and in the server we send these data, and in the response they give the 302 and a URL to the client, and then the client redirects to this URL, which is the ad destination. So wherever we have maybe having some website or some app, whatever, that is the ad destination. So basically, one thing to note here is that we are displaying the ad URL in the client itself. So we send the event to the server, and the server responds with the URL. This is something uh, critical to take a note of, because this is how we would also ensure that the events are not lost. We will discuss it in upcoming slides. Next is the ad. So this is from the advertiser's point of view. So once the advertisers have all the data in the system, how are they able to query from the ad ID? They have an endpoint called get ads, where the query parameter is ad ID, and then we get the metrics, and they also pass in the granularity is fixed, but from and to can be chosen as part of the filter from wherever the UI the advertiser is giving the ad. And in response, they get something like minute, clicks, so on. So that is what we want to build. So if we had something like there is a page that is we have displayed and we have ads on it, and for each ad we had an ad ID and a destination URL on the client itself. And then whenever a click happened, so what happened used to happen. So there are two cases that I'm telling. One is when a click happened, the user gets redirected to the. It won't be called redirect. It would just go to the destination URL destination. There were two steps, and the second step would be a click event sent to the server. But you know what problem can happen in this? The user might go to this event, but there is no guarantee that the click gets reaches the server. Why? Because the user won't click on the ad again. In case the user got the URL, they won't click on the ad. But we want the user to only be able to click on the ad if we are able to track it. You can think it that way. So the second case which we are actually going to design is that the user clicks on the ad. We don't have any URL on the client side, on the website. We have only ad ID. So whenever the user clicks on the the ad ID propagates to the server, and then the server responds back with the 302 and a URL to redirect to. So there is only one step involved, and that is what makes the system robust, and we do not lose any clicks. So this is a very critical point to understand here. So that is why we say the client side redirect can be bypassed and the clicks can be lost. But routing through click means we track every click, and at the cost of one extra hop. So it's just we have one extra hop here, but we are still tracking everything. So let's start with a high level design and see how the data flows in. So we have this web page from where we're displaying these ads. The user clicks on an ad. We have some sort of tick service, maybe for example at the back end. It collects all the ad ID and times impression ID and so on, and timestamp, and it stores it in some sort of DB. It stores it, all of these, and maybe the advertiser just has got some service on its front end, and that using that dashboard the advertiser can simply run SQL queries and fetch from it. So this is a very high level diagram, but you see there is a very it's as I mentioned, it's a naive design, uh, but there are a lot of problems in it. and let's see what the problems are. So every system design problem that we work on, there are some technical challenges that are specific to that problem, right? And that is how the system becomes difficult to handle and difficult to scale. So, uh, but like on a simple terms, you can just say every system design would have one client from where the input happens, then there is a server which handles those input, there is a DB where the input gets stored, and then there is some external downstream service which uses that DB or so on. So this can be a very simple design, but that is not how every system works. Every system design has some technical challenges that are specific to that system. So let's talk about the specific technical challenges that we have in the system. The first technical challenge is that we have a write file rule. What do we mean by a write file rule? It's like a stream of events. It's a continuous stream of events. We don't know that specifically a user would click on one ad, two ads, three ads, or so on. There are so many 10 million ads we discussed at any given point of time, and we have like 10,000 clicks per second. So it's a huge count that to handle with. So it's a write heavy system, and that is the first one. It's a write heavy system. It's a huge scale and it's a write heavy. It's not read heavy. We can call it read heavy. We cannot call it read heavy because from the advertiser point of view, they are not trying to track or view each event. They want an aggregate. They just want the count. So it's not read heavy. As many write events we would be having, we won't be having that many read events. The second is we want to ensure exactly once counting. So for each click, we only want to count it once. We have to ensure that our system, in case of any failure for any reason, it only counts it once. Because double counting would mean wrong billing. So we have to dedupe. Dedupe is if there are duplicates, we just have to take one. So that is what we need to ensure in for the events in the entire system. The third one is real time. So as we said that the advertisers want to view the ads in 1 minute. So we cannot see stale data. So the data has to really pass on through the system quickly, and we have to design it in a way that the queries at the end, when the analytics dashboard is being viewed by the advertiser, the queries run very fast. So that is another requirement. Fourth challenge that might happen is that um, we will have to discuss it in some time, but in case we have our DB, for example, if we are simply using a database, because it's a huge data, 10 million, 10K per second and 100 million per day, so we have 100 million MPs. If we simply use a DB, we'll have to use partitioning. Even though if we use partitioning, we might have a problem like a hotkey problem, which is like if maybe some ad happens for some celebrity, maybe Nike releases some new shoes, so that ad might get flooded for some time during that time, or some big billion day sale happens. So those ads might get clicked very popularly. So they may get a lot of clicks. That would become a hot shot. So that is another problem that we'll have to deal with. That's how we need to design our entire system. So now let's look why our system, a very simple system where we thought we have a backend service, we have a DB, and then the advertisers can query through the DB. Why this does not work? So first problem is this scale. Why it breaks at 10K per second scale? Because if we see, if we have 10K per second, that means 100 million per day. And at any given point of time, the advertiser, if they have to simply apply SQL queries, they would do like select ad ID, something count, and from clicks DB, where time stamp minus current less than equal to 1, group by ad ID. So this entire thing would mean we have to to a full table scan, which is not at all acceptable. It would become a very slow query because querying through an entire database would make it won't help us satisfy this less than 1 second rule. So this solution won't work. We have to think of a better solution. So let's look at another version that we might use, which is instead of a SQL DB, we can maybe use an event store and we can introduce Cassandra over here. And then the click service would dump all of its raw events in Cassandra. And then we introduce Apache Spark somewhere in the system. What it does, we deploy Spark jobs which run over this Cassandra store, and it creates aggregates per minute aggregates, and it stores it in OLAP. And from this OLAP database, this advertiser can run queries and they can see the data. So this is basically a simpler version where we have aggregated data. So queries can be applied on that. It would be quicker than what we have in the simple DB way. But there is one problem that happens in it, and the problem is that when we have Spark, we aggregate it. When we aggregate it, data becomes stale. Like if we run it in 2 minutes or 5 minutes, the data becomes stale. We don't have on the we don't have near real time data. Another problem that happens if some sort of traffic spike happens, then it delays the time in which a Spark job runs. One Spark job would take more time, and then it would take more time in processing the upcoming batches, and that is why more time would be taken, and eventually the data would become more stale. So that is one problem if we use Spark. But so is there a better way instead of Spark? Yes, there is. So what do we do? What we can alternatively do is instead of our just a click service interacting with Spark, what do we introduce? We introduce a Kafka or Kinesis in between. And then what Kafka and Kinesis is, it takes in all the events come in, and they stay here till the time they are processing. So one advantage of Kafka and Kinesis is, for example, if Kafka has got 7 day persistence, so we can ensure when an event stays in there, it stays. We don't lose that event. And then we have Flink. What Flink does is the same as what Spark does, but in an efficient manner. Spark works over batch aggregation. Flink simply works over window aggregation. So per 1 minute, we can just do an aggregation of all the events, and then Flink stores that in OLAP, and that is how the system would become more efficient. So we don't have any stale data. We are not storing it in between. We are not losing any data. So that is how it is helping. Some things that we can note over here is that even time is, because we are using Flink, it is doing on the go. So it's just based on time. It knows when a 1 minute window is safe to close. Spark batch was happening based on batch count, 100 events, so on. But Flink would just close one window, it would watermark the events based on timestamp, and it would know when to close the 1 minute window, and then it would aggregate it. It would keep on aggregating per minute and emit the partials every few seconds in this OLAP database. So that was about how we handle near real time problem. Next is how do we scale writes and handle hot shards. So we discussed that in case there is a celebrity ad flood that can happen at any given time. So we have the click service, this is Kafka or Kinesis that we are using, and then we have Flink tasks that are happening. So how can we make it scalable based on writes? We introduce shards. So each Kafka topic, the Kinesis topic, we distribute it over multiple shards, and how that shard can happen. It can correspond to multiple ad IDs. But still, this happens. So this is for scaling rights. This is for scaling rights. That if we have 10K per second, so we can't just use one partition. We'll have to use multiple partitions, and that is how our scale would be distributed. But then still, there is one problem that happens, which is a celebrity ad flood problem or the hot shot problem. How do we handle that? What we can do is we can sort the hotkeys. For example, if we have whatever is the hot shard key which we have based on ad ID, we further add a suffix to it like O to N to spread the click across shards. So Flink strips the suffix and some reports to overlap. So the when we are storing it, when we are sending it in the Kafka, at that time we add a sorting basically means adding a suffix or a prefix. So we add a suffix and we just program the Flink task in a way that we remove the salt from the ad IDs and they uh, process the aggregation based on that. So just so that our count does not get affected. The third problem was, so we solved three of our problems. The third problem was how do we ensure that each click gets counted only once and we do not count it twice. So what do we do for that? We were talking multiple times about this impression ID. So now let's discuss what that impression ID is. So whenever we place an ad on a web page, we can associate that with an ad ID. But the problem that would happen if we display it on two pages, for example, page 1 and page 2, and we click on that ad. So both there's a possibility that both of them would have the same ad ID and the timestamp. So the server might confuse them and might not know how to separate them. We won't be able to apply any dedupe because we don't have any identifier. How do we identify that this was unique? We can't use ad ID because multiple events can have the same ID because obviously one ad will be displayed multiple times. So we need another identifier. So this is the identifier that we use. We add an impression ID. So what that means is wherever any ad is displayed, that ad gets a unique impression ID wherever it gets. And when that impression ID and when we traverse that click, we pass on impression ID, ad ID, and then timestamp. So whenever this impression ID is going on, we pass that on, and we also introduce a cache in between. This is for capturing the scene IDs. Scene IDs mean that if we have already processed one impression ID, we won't process it again. So how do we do it? We basically, whenever a click service is passing on to the stream, we can either put it here or we can put it also before the Flink tasks. So what happens is whenever the um, event is being passed on from here to the stream, we keep a check. We also keep an entry over here. So when we keep an entry over here, it sees that has that event been passed on. If yes, then we don't need to pass on it again. If it has not been passed on again, then we would pass it on. If it does not exist, we can put a TTL of 1 day just so that we ensure that we don't duplicate the events in that 1 day. We don't need longer time, and we can even keep it smaller, like 1 hour, because we need really fresh data. We don't need to care so much about all of this, and that is how we can ensure to keep a track of the same IDs, and that is how we ensure deduplication. And this is just about how we put it. The impression ID, we sign each ad with the impression ID and then ad ID, and forge clicks. They fail the verification. So in case some attacker tries to send fake clicks to our system, for that we can actually we sign the impression ID plus ad ID using HMAC, and at the server side we verify it using the same principle. If the two don't match, like we would know that what the attacker has sent is a fake one, so we would just discard it. And so, as I mentioned, this Redis can be applied here or at the later stage also, but it is better to apply it before stream so that we can just dedupe early the events and those events don't pass later on to the system. And yeah, that is all. Now, one thing more that we can discuss over here is that at multiple given points, we have chosen a data store. For example, we were having a click service. After that, we chose Kafka or Kinesis. In between, we chose a Redis store. There was also one option that we chose to choose Cassandra. We have not actually used it in the final design, but we can also still talk about it. Then eventually we have Flink tasks over here, and these Flink would store it in OLAP database. Right? We've not discussed S3 data lake, so let's skip it for now. This is basically we use S3 in case we want to also. So this system we built, right? It's real time, but it can still have some problems. So we can also build a reconciliation kind of a system which uses uh, wherein we add in more services which just does a reconciliation of what this real time system calculated is correct or not. But we can skip it for now. So let's skip Cassandra and Data Lake for that. So why do we use Kinesis and Kafka? Because they are durable, they are replayable, and they are sharded. So it can handle a huge scale. Once an event gets entered, it's difficult to lose because it's globally replicable, and it is duplicated across multiple partitions internally by Kafka. We don't deal with it. There is a replication factor that we reduce while configuring Kafka, and similar for cases. So it's a highly durable and sharded system. So we usually use it for streaming, for queuing mechanism. Redis cluster. The advantage of Redis cluster is again it can handle a huge amount of scale. So that is one great advantage. Another advantage is it is in-memory cache. We can also replace with the Redis cluster if you want to make it globally available. But for our system, we might not need this, so we just use a Redis cluster. We just use a Redis instance, and it can handle up to 1 lakh, that is 100K per second. So it's highly scalable and does not impact latency at all. So it's very quick. So that is the advantage. It's a simpler thing to use. We can also use Cassandra, but it would become complicated. It does not offer inbuilt TTL. It also offers inbuilt TTL. So that's the Redis offers inbuilt TTL. A lot of advantages. The next is OLAP columnar. So where we used it after the Flink task, we stored the aggregated data in an OLAP database. OLAP is on online analytics processing. It's OLAP is basically analytics processing DB, like Columnar DB, like BigQuery, Snowflake, ClickHouse. So these are the things where we store them. Uh, so they are specifically for this people. So if you see, there are multiple types of database: SQL, NoSQL. Columnar is one NoSQL database, but it also offers a very distinct kind of features which are appropriate for such a kind of requirement where huge data, aggregated data can be stored and then queries can be run on top of that. So that is why we choose OLAP columnar. S3 we have not discussed, so let's skip it. There's another question that people might come up, or interviewer can follow up from you, that we have millions of ad IDs and advertisers who is sliced by campaign, device, and geography. So columnar, why columnar? Why not time series? So that is the thing. Time series DB have low cardinality, while columnar have high cardinality. That means columnar basically is where you can have multiple columns and you can query data using those multiple columns. So that is why it allows high cardinality, multiple dimensional querying. Time series database is mostly for single metrics, right? Columnar offers multiple columns and we can query over that. Next thing, we already discussed about how we never lose a. Like, so once we have introduced Redis before Kafka and we have ensured nothing gets lost. So after that, Kafka and Flink are very reliable. So they themselves offer that replay on recovery, the 7 day retention, and everything. So all of that is handled by them itself. So at the worst that can happen is in case we lose a message, our system, our server goes down. So we can just replay it. That is the advantage. We do not lose it. We can replay it. So there's another concept that can come in such a scenario is that if we want to ensure, so the system that we've built, it is near real time, but maybe we lose some events. We try to not lose events, but in real life, some sort of loss is unavoidable in terms of events and messages getting lost because of network glitch or some data corruption that might happen. So what if we need a system what if we need a system where we want to reconcile it? That whatever we are storing, is it fine or not? Whatever we are showing to the advertiser, we may also want to build a historical kind of data which kind of fixes all of that, which is very reliable. So, what do we do instead of uh, just storing it in Flink and using Kafka and Kinesis? We store raw events. We store raw events where in an S3 bucket. And then we apply Spark jobs on it, which does a daily recount and stores it again in the OLAP database. And from there, we can simply do a reconciliation whether the data that we stored using Spark is the same and compared to the data that we are getting on per minute aggregate basis from Flink. And this is usually sometimes called as lambda architecture, where we have two types of layer. One is a speed layer from where we are getting data in near real time, and then we also do have a batch layer where we use to reconcile and be sure that whatever data we are showing it's correct. So after discussing all of that, let's have a look at what the final architecture looks like for us. So at, at the final architecture, what we have is we have the ads are placed on the website. They all have one unique impression ID. They get displayed on the browser. Users click on those browsers. The click navigates to the server the and the server responds with 302 redirect. The user gets redirected to the ad. The click is with the click service. The click service queues them on a Kafka queue. In the Kafka queue, we have multiple partitions, and we also have sorted partitions. So, for example, we have A to Z partition, but we also have 0 to N by adding a suffix to the shards to handle any hot shards. Then these events get aggregated via Flink. It picks up a event from 1 minute time frame and then it aggregates it and then it stores that aggregated data in an OLAP database and the advertiser can pull in the data using queries. On the other side, so this was the speed layer. We also built a not so speedy layer, which we call as the batch layer, where we are storing all the events in an S3 lake as well. From the Kafka side, we are storing all the raw events in S3 lake before pre-processing. And other than Flink, we have Spark, which is doing a batch processing over this S3 lake, and it is storing that OLAP, that same data in per day kind of aggregation in the OLAP database, and from there we can run a background job which just reconciles everything and sets up the historical data and also reconciles whether the real time data was correct or not. So this is how our system at the end looks like. And just if we see how the event looks like, whatever, it's the same what we discussed so far. Click happens, it goes to Kafka Flink, OLAP advertiser, so first 302 and the log gets saved. On the second side, we also verify the click service verifies, does a Redis lookup. Here we have Redis. It verifies signature, it's HMAC check, it does Redis lookup, and then writes to stream. This is sharded by add ID, salted if hot. Then the Flink counts by minute, flushes in seconds, and then we have the advertiser that reads from the aggregated OLAP. So now we want to summarize the entire system design into 7 lines. How would we do it? Firstly, we introduce the server-side 302 redirect to ensure that we track every click and we don't lose anything. Everything goes through us, nothing bypasses us. We introduced pre-aggregated analytics. We ensure that we ingest durably, and we used Kafka for that and Kinesis for that to ensure that nothing we don't lose any data. And we also introduced pre-aggregated analytics so that from the reader's side, the advertiser side, we have quicker queries to run on the pre-aggregated OLAP database. Next, we use stream plus Flink. What that gave us, we were able to aggregate our data based on time window, and we introduced a short flash window which helped us keep our data seconds fresh. The next was we tried to eliminate the problem of hot sharding that it got introduced using Kafka. We added salted hot IDs, hot partitions, so that no single shard melts and our data gets distributed across multiple short, salted hot partitions. Next, we introduce impression ID plus Redis Duder. So that is what we used to ensure that we count the ads only once. Firstly, by using impression ID, we introduce a unique identifier, and then we use Redis deduplication to check whether these IDs have been seen or not. Then we use replayable stream plus reconciliation to ensure that we don't lose data, and also eventually we see that the data is correct. So when we are counting these ads, every ad corresponds to money because eventually we want to pay for these click ads to the clients. So we used reconciliation to ensure that the data that we are storing it is equal, it is correct, and that is how we and for that we used Spark, and for real-time data we used Flink. We use columnar OLAP and roll-ups to keep advertiser queries sub-second. So we introduced low latency by using OLAP columnar databases, which help advertisers to view the ad quickly. So that's all for today's video. I hope you liked the video. If this clicked and you know what to do in your next system design, if you get the system design, then like, subscribe, and drop in a comment about how you like it. You can also drop in a comment if you have any system design that you want me to display in the next video. And so till then, keep designing, keep whiteboarding, and take care.